Okay, so today we're going to talk about mobility in WiMAX PnP modes first. Then I'm going to talk a bit about old WiMAX mesh mode, which actually currently doesn't exist. It's just in some textbooks and old standards. It's not used, but it might help you for some other distributed protocols to give an insight about distributed protocols, how they can be done, whatever. Okay. So, in the mobility, a regular device, which is called a mobile station, now the MS, has two additional capabilities over a regular device, which is the power management and the handover. Because now we are more like a GSM domain. Our device is able to move around, but it can be a laptop, it can be a cell phone, smartphone, whatever. So it has to make some changes between base stations, hence the handover. And it has a battery now. It is not connected to the electricity grid, so it has to manage its power. So the power management, there is a there's a mechanism called sleep mode operation in here. So it's basically the device can say that, okay, I have limited battery. I don't think there will be lots of messages coming to me now, so I want to sleep to save battery. Okay? This can also be said like the base station can say that I don't think there will be lots of messages coming to you, so I'm ordering you to sleep. Because we have too many devices in the network, I can't manage all of you at the same time, so you, and you're going to sleep now. So when a device starts to initiate the sleep mode, there are three parameters related to the sleep mode: the Tmin, the Tmax, and the L. The Tmin is when the device is starting its sleep period. It sleeps for this amount of time, okay? The time minimum. Then it wakes up for a period of L. And it queries the server, queries the base station, and saying that, okay, do you have any messages for me during this Tmin period or this secondary L period? If there's no messages in these two periods, it says, okay, I can sleep for a longer period now. So it doubles the duration, 2 times T minus. It sleeps for the second part, so for the second period. Then again, it wakes up for the same period. And it sleeps, the sleep periods getting longer and longer until a maximum of Tmax has been reached. In any part of this scheduling, this thing, a message is received from the base station. The device says that, okay, I'm receiving some messages, so I have to close my sleep mode. So I have to go back to the regular mode, okay? The regular device mode. After that, say after 5 minutes, then the communication is again terminated, and he still wants to sleep, so for whatever reasons. He starts from the scratch, and he starts from the Tmin, and then 2 times Tmin, 3 times Tmin, and so on and so forth. Okay? But this is if there's a message coming from the base station to the device. At any period of the sleep mode, the device has decided to send some message to the base station. It can immediately close the sleep mode, the sleep period, end it immediately, and send the message to the base station. Okay, I'm just getting too ahead of myself, I believe. All right. So that's the power management and the sleep mode. For the handover part, there are 3 different handover mechanisms defined in the WiMAX mesh mode. The regular one, the microdiversity, the fast base station switching. And each one of these methods, they have been completed with 3 steps: the salary selection, handover decision, and the network reentry. Okay, so first of all, what is salary selection? the device, when he wants to make a handover or the handoff, you can use both of them. He first searches around the network and tries to see, okay, if there are available BSs that I can switch to. Okay, for example, I'm moving towards Etiler, so I'm looking for some base stations closer to Etiler. Okay, but there might be multiple of base stations. So they are called the target base stations. The one that I am being served by is called the serving base station. So I'm switching from the serving base station to a target base station, but there can be multiples of target base stations, obviously. But this is just scanning. So the device is still getting its data packages from the serving base station, but it just queries the other base stations in some periods of its time. So it has been conducted with 3 different levels. A device can use either one of them. In the association level 0, there are some random, there are some contention-based slots in the time schedule, so that a device can send these, what was the name? Ranging? No. Scanning packages, let's say. He can do these scanning attempts in these contention-based slots. But consider that there are multiples of mobile stations doing the same thing at the same time. Okay? We are a bunch of people who are on the same bus going to Etiler, and all of our base stations, mobile stations, our devices, are trying to make a handoff to the same base station. So all of them are contending for the same slots. Some of them will succeed, some of them will fail. Okay? The ones who have won the slots will communicate with the target base stations in those slots. Okay? For association level 1, the serving BS and the potential BS coordinate within themselves, and then our current base station, the device's current base station, will say that, okay, this is your dedicated slot. In this slot, you can communicate with the target BS. Okay? There will be no contention. So you are assuredly to communicate with the target base station in this or these slots. In the second one, which is a more complicated and more assuredly with a little less burden on the network, the association level 2, the same thing applies with the level 1, but the response coming from the base station is not sent through the wireless link. It is sent as a regular data package through the backbone. So So we have our serving base station. Whoops. And we have our target base station. And here's our mobile station. All right? So I'm communicating with both of them through the wireless, but they're also connected with a wire because they're base stations. They have electricity, they have regular cables. So I'm sending my request through the wireless link, but my response is sent like this, okay? In association level 2. Association level 1, the request is sent like this again, but the response is also given in the wireless, just the wireless. The serving base station is not included in that transmission. So, okay, the more level you have, the more complex the mechanism becomes, the more protocol intense it is, but the less troublesome for the network point of view. So the second part, after we have decided, the mobile station has decided on which base station it wants to hand over to, then it's just declares its intention to the serving BS, saying that, okay, I'm going to hand over to this base station, number 6. And send some special messages, and after the initiation, all data transmission is terminated between themselves. And then it makes a re-entry, as if it is entering the network from scratch. But there are some, this is like there's the initialization, I think Professor Tuna has told in the last week. There's a long 10 or 11 itemed initialization phase. This is similar to that inside, but it's shortened because our old base station is going to tell some of my parameters, some of these information to the target BS. So I'm not going to tell everything again, okay, to the next base station. Okay. So the second one, the microdiversity handover, this is actually very similar to using repeaters in the network. So in here, consider there are some base stations, and I'm a lucky guy who is inside all of these base stations range. And moving in this direction, okay? So they're all coordinated, and they're always sending the same packets. They're like repeaters, okay? So this is the actual base station. They are only doing the same thing, sending the same packets all the time. So when I'm moving towards them, I can switch between these three base stations whenever I like. Since all of the network parameters are the same, this is like a handover, but it's not like a handover. I mean, you don't send any packets, any control related information among these base stations. But the critical thing is, you know, there might be some devices here and here. This device cannot be heard from the base station 3, and this device cannot be heard from the base station 1, even maybe not base station 2. So the base station 3 is wasting some of its capacity just to make sure that if this device comes into my range within this frame, I have to accommodate for its traffic. But if that guy doesn't come to this direction, that capacity will be wasted. So the network utilization in this case, in the microdiversity, is very low compared to the regular one. So they are synchronized frame structure, blah, blah. For the last one, the fast base station switching, it is in the middle between the microdiversity and the regular one. So it's, the base stations are not like repeaters. They are different base stations. But a mobile station at any given time has this anchor base station, says that, okay, this is my primary base station. These are my, let me write it like a normal regular line. These dashed ones are saying that these are my secondary base stations, okay? So I can make a handoff to them. So they know my working parameters, my operating parameters, my capacities, the capacity of my antenna, transmitters, receivers, whatever, my batteries, so that when I want to make a handover, very little protocol traffic will be communicated between the base stations or the MS and the new base stations, the secondary ones. Are we good on here? Okay. But this is, again, also a little bit history, because the WiMAX, even though the mobility mode, I think it is used for some regions of the world, I hope, but it is not very widely used. So this is just to give you an insight about how, I mean, if you want to make work on a mobility-based protocol, there are options. There are some history, some old protocols like this, who can offer you some options, okay? You can say that if you are designing a protocol, a wireless protocol, or a new wireless protocol has come up, so you can go back to these old things, the Wi-Fi, WiMAX, whatever, GSM, even GSM is old now. So look for some old mechanisms, some ideas, and then take them and use those old ideas to the new protocols, because they weren't bad. The thing is, they couldn't make the markets, they couldn't penetrate into the markets. LTE beat the WiMAX, that's the thing. All right, for the second part, the WiMAX mesh mode. This is not included. This wasn't included in the first WiMAX standard, but it is added in the 16A in 2003. The main difference between the PMP mode and the mesh mode is, in here the subscriber stations, the SSs, can talk between themselves, like the direct link protocol in Wi-Fi. It has that ability. Remember, in the PMP mode, the devices are always communicating through the base station. But here, the devices, if they want, they can communicate with each other if they are within the ranges of each other. Also, the network can accommodate for some subscriber stations that are not directly in the range of the base station, which can be communicated through other mobile stations, subscriber stations. So we can accommodate for these kind of topologies in here. See that the ones say for SS1 and 2 are not in the direct range of the base station. But the base station can communicate with them through SS1 and SS2. Okay, so this is a multi-hop communication. And you see the dashed lines over there between some SSs. So it reflects the fact that these stations can, if they want, communicate with each other. So they have ranges, okay? And there are no physical boundaries, whatever. So this is a mesh topology. This is very messy compared to the PMP modes. We have 2 hop nodes, 3 hop nodes. There can be higher number of hop nodes. So here for some definitions about the mesh mode. Consider the SS5. If some SSs are served by an intermediary node, here like SS8 and 6, no, just 8. Okay, just 8 is served by the SS5. So SS5 is called the parent node of SS8. This is like a tree in data structures. Remember? The leaves, the roots. So the root is the base station. The leaf is the highest hop count nodes. And the one are between are called they are both parents of some devices, and they are the children of another subscriber station. Here, SS5 is the parent of SS8. It is the children of SS1. Okay, but remember, it's not a children of SS2. It's not a child of SS2, sorry. Because it has been decided that the regular traffic coming from the SS5 to the base station will be routed through SS1. It is decided in the initialization. So the ones that the device can communicate within one hop range is called the node's neighborhood. Okay, hence the circle. So this tree, these normal lines, the bold lines, are called the scheduling tree. Okay? And these links are called centralized links. The other ones, the dashed ones, are called the distributed links. Yeah?
The links are decided or they can change? Why some of them are changed?
Well, it is... say for the SS5 case, let's look at the SS5 case. Somehow the link quality between SS1 and 5 is better than the link between SS5 and 2. So at the network entrance, it has been decided that this is a centralized link between 1 and 5. The other one is a distributed link. It can be changed dynamically, but okay, the protocol doesn't allow a dynamic change within its operation. You have to shut the system off and reopen again, or you have to disconnect SS5 and then connect it again and hope that the link will be connected in a different fashion. But there are lots of papers saying that we should switch it dynamically during base station's operation, which has its benefits.
Can't these subscriber stations be mobile?
No, not in mesh mode.
Not in mesh mode?
In mesh mode, they're all static fixed nodes. Yeah, that was important. That's why I'm not saying it like MSs here. They're all SSs, okay? They're fixed. So they're like, this is our region's base station, and these are some apartments, some big buildings. So they are not like personal users, okay? Remember, WiMAX is always envisioned to be like a wireless backbone, a wireless alternative to the ADSL. I think I'm gonna skip this part. This is too much detail for the protocol stuff. Yeah, this is like the connection identifier, which is a bit more detailed. Yeah. So there's some some management messages specific for this mesh mode, which was, I mean, if any one of you is interested in some distributed protocols, do look at these, especially the DSCH, okay? Because it includes some communication between these dashed lines. I'm going to talk about it a little bit in detail in the later slides, but it has very important, very interesting ideas. So the frame structure is completely different from the point-to-multipoint mode in here, in the mesh mode. Again, time is divided into fixed sized things called frames, and every frame has two subframes for the centralized and the distributed. And oops, sorry. So each frame has two subframes: the control subframe, the data subframe. Each subframe is further divided into two parts: one for the centralized, the second for the distributed. So the centralized, it's always about internet traffic, okay? The device, the SS, is trying to communicate with the base station and what is behind the base station. Or, on the other direction, some device outside the network trying to communicate with that SS. For the distributed scheduling, on the other hand, the SSs are communicating with each other within a neighborhood or not. But it's always two SSs in the same network communicating with each other. So the control subframe consists of something called the transmission opportunities, but the data subframe consists of mini slots. They're practically the same thing, but they're just fancy words. So it's like this. This is my control subframe, centralized part of the control subframe, distributed. Okay, skip this coordinate link. This is for the detail. This is the distributed part of the control subframe. The same thing applies for the data subframe. The names just changed, TO to mini slot. So for the centralized, let's first look at the centralized part. It is a little bit similar to the PMP modes. And all traffic is managed by the base station. That is important. The devices are not, they don't have any control over which traffic, which packets it should send at this time. All the control is at the base station. It is all managed by the base station. So it is collision free. But as we can see in our work on this mesh mode, it's inefficient when the maximum hop count is very high. Like 5, 6, even 4 is bad. You have to connect at least at most 3 the number of hops in the network, if you want this scheduling to be efficient. Even 3 is a little bit troublesome. 2 is the best and for the limit. But 3 is also acceptable. So in here, how a device can communicate with the base station. Each childless mesh, this is called a mesh subscriber station. Yeah, I know that's a very terrible words, terrible shorthands. I mean, okay, there's this SSs. Remember, the SS for the PMP mode, the MS for the mobile station, and the MSS for the mesh subscriber station. Yeah, I mean, these are standards. This is normal. So each mesh subscriber station, MSS, or should I can say SS, sends its request to its parent node. Okay, I have this amount of packets to send to the internet. Then each node with at least one child sends its and all of its children's requests that aggregates all of these nodes' requests and send it to its parent node. Up until to the base station. The other direction, when the base station is giving the grants, after getting the requests, the mesh base station generates the grants somehow according to its scheduler. We don't care about the scheduler for the time being. It can be anything. And the grant message is compiled. The grant messages are forwarded to every SS in the network. Okay? So this is important in this mesh mode. Every device in the network knows which device is communicating with which device at which time, at any given time. Okay? So they don't have the local information. Let's say in here, this guy knows when SS2 is going to communicate with the base station, when SS5 is going to communicate with SS3. Every node's information is stored in here, in all nodes actually. So to give an example of this request grant thing, first in here SS6 sends its request to SS4, its parent node. The 4 takes its request and adds the SS6's request and sends it to the SS1. SS1 adds its request to these guys' requests and sends it to the base station. When similar things happen for SS3, 5, since SS2 does not have any child, it just sends its request to the base station. For the grant part, the base station broadcasts the grant to SS1, 2, and 3. SS2 does not have any children, so it does not broadcast it again. But 1 and 3 have children. So they broadcast the same grant message to their children this time. And lastly, SS4 sends the grant message to the 6, so that all the nodes in the network know the complete picture of the scheduling. Are we good in here? I mean, be careful. I didn't use any dashed lines. The dashed lines are not used in the centralized scheduling. Whoops. Okay. For the distributed scheduling part, it is used for intranet traffic, as I said, communication between SSs. And the SSs participate in the scheduling process. The base station is not included in here. So it's like we are settling a debate between some neighbors, okay? We don't want the municipality. There's some loud noise coming from the next apartment building. And I just go there and talk to the guy and say that, okay, this is too loud for me. So I settle my affairs with this guy. So it is settled between us, okay? I don't go to the municipality or the police station and say that my next neighborhood, my next neighbor is having some loud music, whatever. We're just settling it between. So that we don't want, how to say, this is a bit more efficient, because the base station is not dealing with all these smaller internal affairs, okay? because this is not about the internet. It's not about the backbone. I'm sending some FTP packets to my next neighborhood, to the neighboring apartments. Actually, it would make sense if it is deployed in some real life cases. I really want to send some, I don't know, I want to send a movie or a music to a friend in the next apartment without sending it to the internet and then saying that, okay, download this thing from the internet. This is less efficient. But with the Dropbox kind of things, this seems to be not working. So it is again collision-free. So the data and the control packets do not have any chance of colliding with each other. But the request grant process is slower than the centralized scheduling, because there is no single centralized scheduling guy in here. Everybody is inside the scheduling. Okay. So say somehow there is some base station here, we don't care about it, okay? Because the centralized links can also be used as a distributed link. These are just distributed links. These are both centralized and distributed links. So in this topology, I didn't draw the base station, but there has to be a base station for the network to run, okay? Don't think that we can deploy a WiMAX mesh mode without a base station. No. Still, even though we don't use the internet, okay, this is a stupid remark, but we have to use the internet. There should be a base station topology somewhere. So each SS coordinates its control message timings. This is a bit complicated issue. With two hop neighbors. Remember that this is my, oops, where is it? Okay, this is my neighborhood. This guy is in my two hop neighborhood. So I can reach that guy with two links, okay, for the SS8's point of view. I can send the packet to SS4, which forwards it to SS3. So with two links, I can if I can reach a node with two links, it's in my two hop neighborhood or extended neighborhood. For each transmission opportunity in the control subframe, each SS calculates some hash value. And the SS with the highest hash value sends its control message in this transmission opportunity. I think we have some more. So the critical thing in here is there are some transmission opportunities. I want every node wants to send some control messages, which might include some traffic information, might not include some traffic information. So there are some opportunities, and I don't want two nodes to try to communicate at the same time. And then there will be collision, and I have to deal with the retransmissions, what is very troublesome. So with this hash function, each node calculates a number for each transmission opportunity in the future. Say there are 5 TOs in each frame. So each node calculates these hash values, whatever, including their own identities and general key. So that at each TO, one device among all nodes in here has the highest number, which means that node has the opportunity to send its control message in that TO. Is it clear? Because it's a bit complicated issue. Are we good on this? I can give better example, I believe. Say I have these three nodes, SS1, 2, and SS3. And there's this our base station doing nothing at the moment. And we have, like here, okay, 5 transmission opportunities. So for TO1, each node will calculate a number, okay? So SS1 says I am number 1. My identity number is 1. This is the TO number 1, okay? So the TO numbers and the identity numbers are included inside some hash function, and a special key is built, okay? Let me say this is A1, saying for the first TO, okay? TO2 does the same thing, and it will come up with number B1. Sorry, not TO2, sorry. SS2 does the same thing, and it comes up with number B1. SS3 does the same thing and comes with number C1. Whichever of these numbers are the greatest, that node will have the opportunity to send its requests, its control packets in TO1. This is done for all TOs, okay? For some limited future, obviously. It's not done for forever, but it's like, say, for the next 10 TOs, 20 TOs. It is decided based on the protocol.
So those hash functions or the results will be broadcasted to every node in the neighborhood, right?
No. The hash function, each node knows the hash function. This is the unique, this is the same hash function. So each node can calculate. There's no broadcast here because this guy cannot communicate with here. This guy cannot communicate with here too.
But for instance, you calculated your number is 10, whatever, minus 13. So how do you know that mine is greater than you?
Because I also calculate your number.
Okay.
Because the only difference between us is our identification number. Since I know the whole topology from the centralized scheduling, okay, I calculate each node's these numbers at each transmission opportunity and know when which node will talk and when the others will just listen. Okay? But there might be some times that a single subscriber station can dominate multiple TOs based on the hash function. To prevent these kind of occurrences, after an SS has taken a TO, it has an opportunity to send for the it in transmission opportunities, it hold offs for some period. Say number 1 has won here in this TO. And everybody calculates the same thing again. And for the 9th TO, again number 1 has won. But since it has won in the previous 2 TOs, it does not have any right to send another TO in the 9th frame. Okay? It has to hold off for, in this case, 6 TOs. And again, this number is known for all nodes. And again, each SS, even though it cannot communicate with another nodes, knows which nodes will have to hold off between which periods. Okay? So in here, the SS1 calculates its hash function, and it learns that it has the TO0. So it hold offs until 6 TOs because hold off timer is 6. Yeah, I think it's pretty much self-explanatory. Yes? Okay. In another point of view, okay, let's say we have dealt with the non-collision part of the control frames, okay? We know now that there is a collision-free method of sending these control messages. So what should I put inside these control messages so that I can transmit data and receive data, right? So in a control message, each device sends its requests and availabilities. Says that I want to send this amount of data to this neighbor, and I have an availability matrix like this. Based on this request and availability, the grantor also checks its availability, checks these two availability matrices, and takes this request and tries to see at which period this request can be accommodated, which is suitable for both the requester and the grantor. If he hopefully finds a suitable place, it says it generates a grant. No. So it generates a grant, and it sends its updated availability matrix to the requester. The requester also checks the grant again, because you see there's some time between when the request is sent and the grant has come. Between these two time periods, the requester's availability matrix might have changed, so that this request cannot be, let's say that I just called Jam and say that, okay, should we go to a cinema tonight at 1700, whatever. But he has responded in 1 hour. Within that 1 hour, I just fed up waiting for his answer, and I just called another friend, okay? So I have to give him another reply, right? To say that if I'm okay with the schedule or not. This is the second grant part. So yeah. So there's a little bit of detail for this. The availability matrices are like this. Okay. There are some slots. There are some frames. Say there's the future 5 frame, and in each frame there are 5 slots reserved for distributed scheduling. Okay. So the guy, the SS3, says, I want 4 slots of information. Okay, 4 units of information for my transmission. And my availability matrix is like this. I'm occupied in these orange parts, but I'm free on the rest. So he sends this matrix and the request to the SS5. The one on the right-hand side is the availability matrix of SS5. So it adds both of them up and see if it can accommodate the request for a 4-slot period. And it sees that, okay, at slot 4 of the 4 consecutive frames, I can allocate you 1 slot per frame. Okay? But remember, there's an important thing here. The requester doesn't say, I want this amount of slots at each frame. It just says, I want to transmit 1 megabyte of information. It just says the total amount of information, okay? Then the grantor, based on the availability matrices, says, okay, you're going to send 256K in this frame, 256K in the second frame. Something like that. So this is the grant. The grant is also like a matrix. And it adds its new availability and sends it to the requester. The requester takes these 2 things and checks them if they're still available for this grant. If it still is available, it just sends the second grant to say that, okay, the deal is on. We're going to communicate in the 4th slot in the 4 upcoming frames. Are we good in here? This was a very complex thing, by the way. As far as I know, there are very few other distributed mesh-like wireless protocols. I mean, there's a big topic about the MONETs, the mesh ad hoc networks, which whose importance has been waned in the last a few years now, as far as I believe. It was a very big thing when I started the MS, I think 2004, 2006, in those periods. But now it's like people are very skeptical about it. There are tons of papers, and new people doesn't want to do some research on this MONET stuff. But during those research, there are just a couple of protocols for wireless mesh networks have been built. One of them is the WiMAX mesh. That's why the importance of this is a solid protocol. Okay, it has its problems, obviously. I mean, I can talk for them about ours. My MS thesis is about that, so we have made some changes about this request grant schedule. There are lots of unaddressed issues in the protocol, in the standard. Sorry, the standard is like about, I remember, 900 pages long or something like that, and it was badly written. Whatever, but I mean, keep that in mind that this is a solid example of how a protocol can be built for a mesh node, wireless mesh node. Finally, for the initialization part, I'm going to talk about the initialization in the mesh modes, which is a bit different from the PMP modes. So first, the guy sends, it is again very detailed. This is a little bit shorted, summarized version. So there are these messages called the NCFG, the network configuration packet. So it sends the device, when it wants to connect to the network, it sends these packages and learns some network time, where the base station is, whatever. So it gets some downlink channel, tries to see if there's some transmission, some downlink transmission in this frequency band. There might be multiples of frequency bands, multiples of WiMAX mesh networks at the same physical location. So then, if it finds a downlink channel in a network configuration packet, then it gets this information from the network configuration packets and tries to build some physical neighbor lists. And see, there's this potential sponsor node. Remember, each node has a parent node in this topology. So from the network configuration packages, which includes the whole topology information, it tries to see which nodes I can connect, which nodes can be my parent nodes. Okay? Then, after seeing the potential parent nodes called the sponsor nodes, it sends its request to these sponsor nodes to say, okay, do you sponsor me to join the network? Can you vouch for me? Can you say, okay, I'm a new node, and this sponsor node will say to the base station that, hey, base station, there's a new node trying to connect through me to you. Okay? That's the intermediary guy. After the device is decided on a sponsor node, you see in the second part there can be multiples of sponsors. In the third one, the device selects one of those nodes to be the actual sponsor. Then it negotiates some of its capabilities, bandwidth information, I don't know, channel information, everything, authentication information, whatever, through this sponsor node to the base station. Because the base station, at the end, the base station will decide if the node's to be connected to the network or not. It can say that I'm overloaded, I don't want any other nodes, or your security credentials are not good. You might be a fake, you might be an interloper, some hacker, whatever, some banned user that I don't want you in my network because it is the base station's network. But the sponsor node just acts as a relay station. Okay. The authorization is also done, and then the node is registered to the network topology. Some IP is taken. There's this funny name, established time of day, which gets the time of day from network. I don't know why they put it in the standards. This seems so, insignificant, but I don't know. So there's this operational parameters which gets the link IDs, whatever, these kind of network-specific information is given in this part, and that is completed. If there are no problems in this whole 9-step initialization procedure, then the node is included in the network. It has a parent node, and it has some distributed links. It has a centralized link, so that it can communicate with the base station and the other nodes in the network. Okay, that is. Sorry, there are two more, and the neighbor link, the distributed links are formed up in the 11th. I'm sorry. That. So it's roughly how the
How the other nodes or the existing nodes in the network realize that the new upcoming member is coming or new member has joined already?
There is this, you see the one in the top, MSH NCFG, network configuration. This is a periodical broadcast message, which is sent by the base station and forwarded to all nodes from the intermediary nodes. Initially, most of the nodes will not know about the new node. But after some time, the next NCFG message will be broadcast. All the nodes in the network will know the new topology. Then they understand, they learn about the new node's existence. This is the network entry, NENT, and the initialization, the network configuration stuff is done with these two control messages. I mean, these are related to, there are 4 control messages here. These are related to the network configuration. The DSCH is for distributed scheduling. CSCH is for centralized scheduling. If I should go to this small list in here. Yeah. The first one is for network configuration, distributed scheduling, centralized scheduling is for centralized scheduling configuration, and this is for the network entry. But I didn't go into detail about all of these things. It is very messy and it will take time, which is not important. One of the biggest problems in the mesh mode, similar to the PMP mode, is in the standards there weren't any BS schedulers defined. The standard just say that put any scheduler you want. You are free. It is for vendors to decide what kind of a scheduler you will put in here. So there were tons of papers about saying that this is a BS scheduler for WiMAX mesh modes, journals, conference papers, lots of them, saying that this is good for centralized scheduling, this is good for distributed scheduling, this is good for, I don't know, this is more fair than the others, this leads to higher link utilization, blah, blah. And after a while, some very advanced schedulers also come up, which named space diversity, because we have a critical thing here, which we did not cover. You see, normally, these links are too far away, right? Say, theoretically, if SS4 is communicating with 6, and at the same time BS is communicating with SS2, there won't be any significant interference because they're too far away. But the protocol prohibits these kind of things, saying that you can't be sure about these interference things, so let's stay at the safe side and ban these kind of special temporal things, which leads to significant link utilization problems. Because this is a rather nice topology. But think about a very strange topology, like there is the base station, the SS1, SS2, SS3, SS4, and even SS5, which is like this. If we want to obey these rules, we will lead to very terrible link utilizations. Okay? So mostly based on these kind of topologies, people start to talk about, okay, we have to do some space diversity multiple access schedulers, which allow multiple transmissions at the same time, which are very far away in space, so that they don't cause an interference between themselves. They are very good solutions, but they are very complex solutions, and you have to change the protocol. That was the problem. That was the biggest problem. Because then you have to go to the vendors, you have to go to Nokia, Siemens, Huawei, whatever, and say that, okay, you have to update your firmware at least. So I don't see any real devices which include these kind of things. But I mean, theoretically and actually, if they put in some real-life situation, there will be real-life benefits in utilizing these kind of techniques. So this is an important idea. Okay, I think that sums up pretty much everything I can say about the mesh mode.